When you think about chemistry, what comes to mind? Probably beakers and labs, right? But what if I told you it's a lot more like building with Legos, tiny molecular Legos? That's what we're diving into today. How chemists actually build the molecules that shape our world from the ground up. I mean, think about it. How are new medicines or super advanced materials actually made? It seems so complex. But the secret is that it all starts small. I mean, really small. It all starts with the art of building exactly the right molecule, one atom at a time. And the star of our show today, our favorite Lego piece, if you will, is something called a heterocycle. All that means is it's a ring-shaped molecule. But here's the twist. It's not just made of one thing, like carbon. It's got a mix of different elements in there. These little rings are the absolute core building blocks for so many things. Drugs, dyes, you name it. So learning how to make them, that's a chemist's superpower. All right, so here's the game plan. We're going to cover the art of making these rings, look at a couple of key ingredients, hydrozones and Schiff bases, then we'll check out this amazing molecular scaffolds called chalcone. And we'll wrap it all up by talking about why any of this matters in the real world. Sound good? Let's get started. Okay, first up, building with hydrozones. Think of this as our first set of recipes from the molecular cookbook. We're going to start with an ingredient called a hydrozone, specifically benzoyl hydrozone, and see how we can use it as a base to cook up some really cool five-membered rings. All right, so here's our first challenge. You see those two simple molecules at the top? The goal is to get them to combine and form that neat little ring at the bottom, a 1,3,4-thiodiazole. But how do we get from A to B? What's the magic that makes this happen? Well, it's not magic, it's just really elegant chemistry. It happens in a few steps. First, the two pieces connect to make one long chain. Then, that chain kind of starts to curl up on itself. And here's the key moment. One end of that chain reaches over and attacks another part, closing the loop. Bam, you've got a ring. To finish it off, a tiny water molecule gets kicked out, and that locks the whole thing in place, making it nice and stable. And there you have it, the final product, a stable 1,3,4-thiodazole ring. And the name actually gives you a hint of what's inside. Thia is chemist speak for sulfur, and aza is for nitrogen. So the name literally tells you there's a sulfur and two nitrogens in that five-numbered ring. Pretty cool, right? Okay, now this is where it gets really interesting. Check this out. We're starting with the exact same hydrozone molecule in both of these reactions, but look at what we end up with. They're different rings. One has a sulfur atom in it, the other has an oxygen atom. So what gives? How did that happen? It all came down to the second ingredient. That's it. It's just like baking a cake. You follow the same recipe, but in one batch you use vanilla, and in the other you use lemon extract. You get two totally different cakes, right? It's the same thing here. You use a partner molecule with sulfur, you get a sulfur ring. You swap it for one with oxygen, you get an oxygen ring. One tiny change, a completely different outcome. That's the power of this. All right, let's switch gears. We're moving on to our next strategy, reacting with things called Schiff bases. This is a totally different path, and it's going to let us build some even more complex structures. The cool thing about this method is that you can build what are called fused rings. Imagine two rooms in a house that share a common wall. That's kind of what this is. Two rings stuck together. And just like before, you can see how a simple tweak lets you build one with an oxygen atom or swap it out for one with a sulfur atom. So versatile. And it doesn't stop there. Change the partner molecule again. Here, we're using something called an alpha haloketone, and poof, you get yet another different fused ring. It really is like plug-and-play chemistry. You just mix and match your building blocks to get exactly the structure you want. Okay, so we've seen some cruel recipes, but now it's time for the main event. What if there was a molecular master key, a single starting molecule that could be used as a scaffold to build a ton of different rings? Well, there is, and its name is chalcone. And here it is. This is chalcone. You see that specific pattern of atoms and double bonds? That's its secret weapon. It creates all these little hot spots on the molecule, places that are just begging to react with something. This makes it the perfect, flexible scaffold for building all kinds of stuff. So let's see this thing in action. We're going to take our chalcone scaffold, and we're not going to change it. We're just going to change the one other molecule we mix it with. Get ready, because we're going to see a bunch of different outcomes, one after the other. Okay, first up, chalcone plus cyanoacetamide. Boom!
You get a pyridine ring. This is a big deal. It's the core of things like niacin, vitamin B3.
Next, swap that out for urea. The chalcone scaffold does its thing, and now you have a pyrimidine ring. We're talking about a key piece of DNA and RNA here. Super important.
All right, next one. Mix it with hydrazine. Now you've got a pyrazole. That little ring is the backbone for major anti-inflammatory drugs. See the pattern? And one more. Use a tweaked version of hydrazine, and you get a tweaked pyrazole. It's amazing, isn't it? One scaffold, and just by changing its partner, you can build a whole library of different useful molecules. It's just an incredibly efficient way to create. So, okay, we've seen a lot of how this all works, but now let's talk about the why. I mean, why do chemists spend so much time and effort figuring out these recipes? What's the big picture? Well, if you've been paying attention, you might have noticed some patterns, some rules of the game that kept popping up. You have atoms with lots of electrons attacking atoms that need them. You see that nature really seems to like making these stable 5- and 6-membered rings. And you almost always see a little molecule like water getting kicked out at the end to make everything permanent. This isn't random. This is the chemist's playbook. And this playbook is so important because every single new ring, every new molecule a chemist builds is a potential solution to a real-world problem. It might be the next life-saving antibiotic, a part of a new solar panel, or a super strong new material. These drawings on a screen, they lead directly to real-world breakthroughs.
It really is kind of mind-blowing. It all starts with just lines on a page, right? A blueprint. But using these incredibly clever and logical reactions, chemists can turn that simple drawing into a real, three-dimensional thing, a molecule that can actually go out and do something to shape our world.
So the big takeaway is this. None of this is an accident. Every one of these rings was designed, built with purpose. It's a combination of pure creativity and hard logic. Which leaves us with a really exciting final thought. As chemists get even better at building with these molecular Legos, what problems are they going to solve next? What are they going to build for us tomorrow?